Good day, everyone. So nice to see you after the break. Previously, we started to study L functions of Dirichlet characters, and today we are going to prove functional equations. For L as chi. Let me remind you that we have chi, which is a function from natural numbers to complex numbers. Chi is a Dirichlet character, which means that chi AB is chi of A, chi of B, and also chi of n plus q is equal to chi of n. And we also discussed some notions of primitivity and notion of Dirichlet character modulo q. Periodicity is not enough. Sometimes you need to require something else. Okay, and we also discussed the connection of Dirichlet characters and the corresponding L functions to the distribution of prime numbers in arithmetic progressions. Namely, we established that Dirichlet theorem on primes in arithmetic progressions follows from the relation L1 chi is not equal to 0. So we did not establish this non-identity for all characters, but we proved that for any modulus q, we have at most one real character such that L1 chi is equal to 0. And today I would like to not prove this relation. We will prove it during the seminar. And I would like to focus on functional equations and analytic continuations. What do we know about L as chi? We know that L as chi is holomorphic for sigma greater than 0, right? If chi is non-principal. And to prove the functional equation, I first would like to do some harmonic analysis on the cyclic group, because your Dirichlet character can be considered as a function on C over QZ, and so you can do some harmonic analysis. So the first thing is harmonic analysis. On Z over QZ. So suppose you have some function f from Z over QZ to complex numbers. Then you can define some other function on this group, which is called the Fourier transform of your function. Okay, this is a definition. Fourier transform f hat of f is the following thing. It is f hat of n, which is 1 over q, sum over all m from 0 to q minus 1, f of m multiplied by e to the power minus 2 pi I n m over q. And now we are going to see that this Fourier transform is very similar to the Fourier transform on the real line, in the sense that we have the similar formulas like Fourier inversion and Parseval identity. Let us establish these formulas. This will be the first theorem for today. Theorem 1, inversion plus Parseval. For any f from our group to complex numbers, we have, first of all, let us denote it by A, the inversion formula. F of n is equal, well, it is almost equal to the Fourier transform of the Fourier transform, up to one factor and one change of sign. F of n is equal to sum over all m from 0 to q minus 1, f of m, f hat of m, sorry, multiplied by e to the 2 pi I n m over q. So it's the same formula, but you have the Fourier transform inside the sum, you have plus in the exponent, and you have no factor outside of the formula. Okay, and the second statement is that sum over all n from z over qz, absolute value of f of n squared is equal to the sum over all m from the same group of absolute values of your Fourier transform squared. Is the statement of theorem 1 clear? Okay, so today we are going to see why this theorem is useful in studying Dirichlet characters. In some sense, what? Okay. In some sense, this might sound a bit unnatural because, well, Dirichlet characters are kind of functions on z over qz star. So they are multiplicative characters. And here we are clearly doing some additive mathematics, right? Because we have additive characters of our group.
What about this star?
Once again, chi is kind of a function on z over qz star. So it is a function with multiplicative properties. And here we are doing some additive stuff because we have additive characters of z over qz. Okay, but it turns out that this interplay between multiplicative and additive structure is very useful and even beautiful. Okay, so first let us prove the first formula. Well, f hat of m is equal to 1 over q, sum of all k from 0 to q minus 1, f of k, e to the power minus 2 pi I, amk over q. So sum over all m from 0 to q minus 1, f hat of m multiplied by e to the power minus 2 pi I and m over q is equal to the following. So we are going to get
plus.
plus. We are going to get a double sum. So it is the sum over all m from 0 to q minus 1 1 over q e to the power 2 pi I n m over q, sum over all k from 0 to q minus 1, f of k multiplied by e to the power minus 2 pi I mk over q. Correct? Okay. Now you can probably guess what we shall do next.
Just change the order of summation.
So this is the main kind of trick in analytic number theory, is that you can change orders of summation. So you get the outside sum over all k from 0 to q minus 1, f of k divided by q, and then you have the inner sum over all m from 0 to q minus 1, e to the power 2 pi I m n minus k divided by q. This is because we kind of joined two exponents together, right? Okay, so now we need to evaluate this inner sum. And this evaluation is, of course, completely trivial because the sum over all m from 0 to q minus 1 e to the 2 pi I m r over q is equal to what? Well, this is a geometric progression. No.
Just.
So this is a geometric progression. So we get 1 minus e to the power 2 pi I r over q multiplied by q, the number of terms, and divided by 1 minus e to the 2 pi I r over q. Right?
Mm-hmm.
And the numerator is equal to 0 always.
Mm-hmm.
Because you get 1 minus e to the 2 pi I r. But sometimes your denominator is also 0. So you get 0 if r is not congruent to 0 modulo q, and q if r is congruent to 0 modulo q. Of course, the second part is easier to establish if you note that if r is divisible by q, then all of these exponents are equal to 1.
Mm-hmm.
But also you can, you can, for example, use L'Hopital rule, right? So you can assume that r is actually a real number, then you can send your r to 0. Okay, so our inner sum is equal to 0 if n minus k is not divisible by q, and to q if it is divisible by q. So this sum actually contains only one term. The term with n equals, the term with k equals m. So you get f of m divided by q multiplied by q. This is equal to f of m, which concludes the proof of the Fourier inversion formula. Okay, also an easy remark. This part of our theorem shows that the functions of the form n goes to e to the power 2 pi I m n over q form a basis of functions on z over qz. This is, of course, a very general fact. If you, for example, take a finite abelian group, you can prove the same. If you take, say, compact compact Lie group, you can prove the same. Okay, so this is a very particular case of some representation theory. And now let us establish the second formula. Nice. It's of course B, but not B. So the sum of all m from 0 to q minus 1, absolute value of f of m squared, f hat of m squared, is equal to sum over all m from 0 to q minus 1, and then we write our formula once again. Absolute value of 1 over q, sum over k from 0 to q minus 1, f of k, e to the power minus 2 pi I mk over q squared. And then we expand the square and we get a triple sum. So we get sum over all m from 0 to q minus 1, 1 over q squared, and then we have sum over all k1 and k2 from 0 to q minus 1, and then what do we get? So we should take our sum and multiply it by the conjugate sum. So we get f of k1, then f of k2 conjugate, then e to the power minus 2 pi I k1 m over q plus 2 pi I k2 m over q. Right?
Может, мы сразу соберем скобочки, чтобы красиво было.
Okay, so let me continue this. This is the sum of all k1 and k2, f of k1, f of k2 conjugate, 1 over q squared, then, I think I missed something here. So there should be 1 over q, of course. You should not forget the Norman factor. Okay, so here you get sum over all m from 0 to q minus 1, e to the power 2 pi I m k2 minus k1 divided by q. And this sum is equal to 0 if k1 is not equal to k2, and to q if, sorry, this is once again incorrect. I'm very sorry. This should be q. Yeah, now everything is fine. Okay, so this sum is equal to q if k1 is equal to k2 and 0 otherwise. So you get 1 over q, sum over k, f of k squared.
We got 1 over q.
Yeah, but you have sum of Fourier transforms on the left.
Yeah.
So you should multiply it by q. Okay, so first of all, if you know everything about Fourier transform of your function, you know everything about your function, and in particular, if you know the L2 norm of your function, then you know the L2 norm of Fourier transform and vice versa. Next, we can use these formulas to establish the Fourier expansion of Dirichlet characters. But we are going to do it only in the primitive case. When the character is not primitive, the formulas will not work. Let me remind you that chi modulo q is called primitive if it cannot be induced by a character chi1 to a smaller modulus q1. And by induced, I mean that chi of n should be equal to chi1 of n if n and q are coprime. So this, of course, once again corresponds to induced representations, right? So you can always induce a character from a subgroup to the whole group. Sorry, no, this does not work this way, right? Your subgroup also should be a factor group. So this is a different construction. So once again, if you have a group and its quotient, then you can induce character from the quotients, from the quotient to the group. Okay. An example of a primitive character is, for example, Legendre symbol modulo phi. And non-primitive character, well, lots of non-primitive characters. For example, any principal character is not primitive, modulo any q greater than 1. Okay, so now we are going to establish the second theorem, Fourier expansion of primitive characters. So let me write this as follows. If chi is primitive modulo q, then we have the following formula. I will write down the formula we are going to use. Chi of n is equal to 1 over tau of chi bar, sum over all m from 0 to q minus 1, chi bar of m multiplied by e to the power 2 pi I and m over q. So now I need to explain what is tau. Tau of chi bar is equal to the sum over all n from 0 to q minus 1, chi bar of n multiplied by e to the power 2 pi I n over q. This is called the Gauss sum. Also, and this is very useful, absolute value of tau of chi and also of chi bar, of course, is equal to square root of q. So let me clear something out. So chi hat of n is equal to chi bar of n divided by tau of chi bar. And this is kind of a surprising formula because it turns out that if your function is multiplicatively structured, then its Fourier transform is rather small. So every value of your Fourier transform is at most 1 over square root of q in this case. Okay, so let us prove this formula. How do we do it? So if n is invertible modulo q, that is the greatest common divisor of n and q is equal to 1, then take n star such that n star is congruent to 1 modulo q, and let us look at this sum and make a change of variables and consider sum over all m from 0 to q minus 1 chi bar of m e to the power 2 pi I n m over q. This can be transformed using linear change of variables. So you can always change m to say n star k. If you set m to be n star k, then when m runs over all residues modulo q, k also runs over all residues modulo q, right? Due to invertibility. So you get sum over all k from 0 to q minus 1, chi bar of n star k, and also you get e to the power 2 pi I n star k divided by q, right? So chi bar of n star k is equal to chi bar of n star multiplied by chi bar of k, and this is just chi bar of n to the power minus 1 multiplied by chi bar of k, and this is the same as chi of n multiplied by chi bar of k, right? Due to the fact that chi of 1 is equal to 1, and also chi is always a root of unity. Okay, and also e to the power 2 pi I n star k divided by q is the same as e to the power 2 pi I k over q. This is because n star is congruent to 1. So this sum is actually equal to chi of n multiplied by the sum over all k from 0 to q minus 1, chi bar of k multiplied by e to the power 2 pi I k over q, which means that this is chi of n tau of chi bar by definition. Okay, so this concludes the proof if your n is invertible. And now we need to prove that this sum is equal to 0 if your n is not invertible.
А можно, пока мы очень далеко еще не зашли, напомнить, как у нас хи работает?
Что значит?
То есть мы просто взяли какую-то произвольную мультипликативную периодическую функцию, так?
Не совсем. Мы еще потребовали, чтобы, во-первых, она была равна нулю на всех остатках, которые не взаимно просто с q, а во-вторых, чтобы она не приходила ни из какой такой функции по меньшему модулю. Первое, это означает, что это характер Дирихле по модулю q, а второе означает, что это примитивный характер Дирихле по модулю q. Пока что мы ничем из этого не воспользовались вообще. Воспользовались только мультипликативностью и периодичностью.
Мяу.
Okay, so now we need to prove that if your greatest common divisor is greater than 1, then we have the following. Sum over all m from 0 to q minus 1, chi of m e to the power 2 pi I e to the power 2 pi I m n over q is equal to 0. Chi bar, sorry. Right? Because we have in our identity chi of n on the left. Okay, so how do we proceed? We have
Didn't we just prove this idea?
no, we only proved it if n is invertible. And what do we do if n is not invertible? Then we need to do something else. So if n and q are not coprime, this means that you can multiply n by some divisor of q, some proper divisor of q, and get 0 modulo q, right? D dividing q, d less than q, such that md is congruent to 0 modulo q. Right? This means that if say m is congruent to 1 modulo d, then nm is congruent to m modulo d. Right?
Then it's congruent to n.
Modulo q,
I think that's right.
modulo q and congruent to
N.
to n, yeah. Oops. To n modulo q. Okay, so what do we do next? Well, choose k congruent to 1 modulo d. Take any such k. Then e to the power 2 pi I m n over q, which will be equal to e to the power 2 pi I m n k over q. Right? Because mk is congruent to m. Nk is congruent to n. So m and k is congruent to mn. Right?
Сейчас еще раз можно?
Nk is congruent to n modulo q. So m and k is congruent to mn modulo q. Correct? So now we continue our computation. Sum over all m from 0 to q minus 1, chi bar of m, e to the 2 pi I mn over q, say it is equal to s. Then the same sum is equal to the sum over all m from 0 to q minus 1, chi bar of m, e to the power 2 pi I m n k over q. By definition, if k is invertible, modulo q, then we have what? Then sum over all m from 0 to q minus 1, chi bar of m, e to the 2 pi I m n k over q is equal to chi of k s by the same change of variables, right? You need to divide your variable by k, and then you get chi bar of 1 over k, which is chi of k. Correct? Hence, if s is not equal to 0, then chi of k must be equal to 1 for all k which are coprime to q, with k congruent to 1 modulo d. Right? Now let us define psi of n as follows. Psi of n is equal to 0 if n and q over d. Sorry, no, q over d is incorrect. If n and d are not coprime, and it is equal to chi of m if n and d are coprime, and m is congruent to n modulo q, m and q are coprime. So for any residue modulo d, for any number which is coprime to d, you can find a number which is coprime to q, and also congruent to your number modulo d, right? This is due to, say, Chinese remainder theorem. So this function will be a Dirichlet character modulo d. Psi is a Dirichlet character modulo d, and psi induces chi by definition. Any questions? So once again, if our sum is non-zero, then for any k which is coprime to q and congruent to 1 modulo d, we have chi of k is equal to 1. This actually means that your character does not kind of essentially depend on your residue modulo q. It depends only on your residue modulo d, in certain sense. So you can define this function psi of n. This psi of n is clearly a Dirichlet character, and it is by definition the Dirichlet character inducing chi. And this is a contradiction because chi is primitive.
I thought that in this sense chi induces phi, not the other way around.
Of course, because the characters modulo smaller numbers can induce characters modulo larger numbers, not vice versa, right?
So smaller number induces bigger.
Correct? If you have a character modulo, say 9, you can induce a character modulo 27 trivially, right?
Yeah,
Okay. Now what? So we established our formula, and what do we want now? Well, we proved that certain sum is equal to chi of n multiplied by some number. We need to prove that this number is non-zero, right? Because otherwise we cannot divide and we get some trivial identity. So by our formulas, the Fourier transform of chi of n multiplied by tau of chi bar is equal to chi bar of n, right? No, it's something is incorrect here. Yeah, of course. Lots of stuff incorrect here. So, what did I prove? It's still right. So we know that that if you multiply your character by this Gauss sum, then it has an expansion in terms of this exponential sum, and they are equal to tau of chi multiplied by no, this is still false, but okay. So what did we prove? We proved that basically this this Fourier transform is equal to chi of n bar divided by tau of chi bar, right? And by Plancherel formula, we know that chi bar of n absolute value squared is equal to 1 over q sum over all m absolute value of chi of m squared. This sum is equal to phi of q. This is phi of q divided by q. And this sum is equal to phi of q divided by absolute value of tau of chi bar squared. This is still not a proof that this sum is non-zero, but you can establish that Gauss sum is always non-zero by expanding the corresponding formula actually. So you do not need to use the Plancherel formula, but this identity is actually one of the phases of Plancherel's formula. Okay. For instance, during the seminar, we will establish a completely explicit formula for the Gauss sum of the Legendre symbol. So you can easily prove that if chi sub p of n is equal to Legendre symbol of n modulo p, then if p is congruent to 1 modulo 4, then tau chi p is equal to plus minus square root of p, and if p is congruent to 3 modulo 4, then tau of chi p is equal to plus minus I square root of p. And this thing with plus or minus is actually trivial, but if you want to establish the formula without a plus minus sign, then it becomes a nice problem. Okay, now let us use our Fourier expansion to prove something non-trivial. First of all, let us establish the Poya-Vinogradov bound. This will be very fast. Poya-Vinogradov bound. So suppose you have chi primitive modulo q, and what do we want? We know that we know the following fact, that m of chi, which is maximum over all t, absolute value of sum over all n less than or equal to t, chi of n, is finite, right? So the complete sum of your character of all numbers from 0 to q is equal to 0. So if you consider any larger interval, you can cut chunks of size q, and then you are left with some remaining interval of size at most q. So actually we know that m of chi is at most q. It turns out that using Fourier transform, one can get a much better bound. Where Vinogradov. And it is also known that this bound I'm going to prove is somewhat sharp. You cannot do much better than what we are going to prove. For any primitive q, primitive chi, sorry, modulo q, we have the following. M of chi is less in order than square root of q multiplied by logarithm of q. So sum of your character over any initial segment is at most square root of q multiplied by logarithm of q. As to the sharpness, it is known that if generalized Riemann hypothesis is true, then you can replace square root of q log q by square root of q log q. And it is known that this is unimprovable. Square root of q log q is yes. So you can construct some characters and natural numbers q such that m of chi is at least square root of q log q with some constant, of course. So let us prove this theorem. But first we need to prove the following very simple lemma. For any alpha which is real but is not an integer, and for any n, we have sum over all n less than or equal to n, exponent of 2 pi I n alpha is at most 1 over this symbol of x, which is not the norm. This is the distance to the nearest integer. Minimum of x minus n, where n is an integer. So this is a distance from your x to the set of all integers, which is closed. So this is a non-zero quantity here, right? Actually, it is minimum of fractional part and 1 minus fractional part. So, okay, if you have any, not x, alpha, sorry. So for any alpha, you can estimate the sum as follows. One can notice that this does not depend on n at all. The proof is very simple. Sum over all n less than or equal to n. This is once again the geometric progression.
Сейчас там 1 делить на вот этот
Расстояние от альфа до ближайшего целого.
Вот там альфа там.
Альфа. So you get e to the power 2 pi I alpha minus e to the power 2 pi I n plus 1 alpha. We assume that n is an integer, of course, divided by 1 minus e to the 2 pi I alpha. Now let us take the absolute value, and now what we are going to see? Well, in the numerator you have this term, e to the power 2 pi I n plus 1 alpha. Since we do not control n, we know nothing about the value of this quantity, right? So the only bound we can hope to get here is 1 plus 1, right? So this is at most 2 divided by 1 minus e to the 2 pi I alpha, correct? And this thing in the denominator can be rewritten as 2 over e to the power pi I alpha minus e to the minus pi I alpha. So this is equal to 1 over absolute value of sine pi alpha. And then you can easily check, please do it, that this is of order at most distance from alpha to the nearest integer. So of course sine pi alpha is 0 at all integers, and 1 over and absolute value of sine pi alpha is actually dominated by the distance to the nearest integer. Okay, so let us prove the Poya-Vinogradov theorem.
Сейчас. Можете чуть-чуть подвинуться, с вами просто не видно самого конца. Спасибо.
Ничего не произошло, геометрическую прогрессию раскрыли.
Ну, вопрос в том, как. Ну и потом к чему это свели, потому что...
Okay, let me draw a picture here. So, sine pi alpha goes like this. 1/2, 1, and it goes like this. And the distance to the nearest integer goes like this. So you can clearly see from the pictures that the ratio of these two things is actually bounded. Well, also by something obvious, right? Like 2 or something, right? Okay.
So why is 1 minus e to the power of 2 I alpha equals to this one?
So here first I replaced the thing in the absolute value by the opposite thing. So I moved it here, right? And second of all, I multiplied it by e to the power minus I pi alpha, which is of absolute value 1. Correct? Okay, so let us prove Poya-Vinogradov bound. Well, sum over all n less than or equal to t, chi of n is equal to sum over all n less than or equal to t, what now? 1 over tau of chi bar, sum over all m from 0 to q minus 1, chi bar of m, e to the power 2 pi I and m over q, right? So this is equal to sum over all m. Now from 1 to q minus 1, because the term with m equals 0 does not appear here. So we get chi bar of m multiplied by 1 over tau of chi bar, sum over all n less than or equal to t, e to the power 2 pi I m n over q. And then for this last sum, we apply our lemma. So this is at most 1 over square root of q, because of the absolute value of Gauss sum, multiplied by the sum over all m from 1 to q minus 1, 1 over absolute, not absolute value, distance from m over q to the nearest integer. And now what is this distance? If m is at most half of q, then it is just m over q. And if m is at least half of q, then it's q minus m over q. So this is at most 1 over square root of q, sum over all m less than or equal to half of q, q over m. And this is once again a harmonic number, so this is at most square root of q log q, which concludes the proof. So using the Fourier expansion, we actually get something very non-trivial for the sums.
Сейчас еще раз. Можно, во-первых, объяснить, откуда у нас корень из Q взялся?
Это
Ну, 1 делить на корень из Q.
Вот эта штука по модулю корень из Q. Это мы знаем.
Ладно. Так, а потом вот переход. А, все.
Сработало?
Сейчас. Вот последний переход, который... Ладно, не последний, предпоследний. Второй в нижней строчке. Где мы избавились как раз, да, вот этот.
Once again, if m is at most half of q, then you get q over m. And if it is at least half of q, you get q over q minus m. This is the same thing, but for q minus m. So you get the same sum twice. That's it.
Okay, so now we are going to use this Fourier expansion for even more non-trivial stuff, and let me formulate the theorem, the functional equation. Let chi be a primitive character modular Q, and delta be equal to what? To 0 if chi of minus 1 is equal to 1, and 1 if chi of minus 1 is equal to minus 1. What is chi of minus 1? Of course, chi of minus 1 is just chi of q minus 1 due to periodicity. Any Dirichlet character can be continued to a function on all integers using this value at minus 1. And you either get an odd function or an even function. So this delta is kind of an oddness of your character. It is equal to 0 if character is even, and at 1 if it is odd. Define now psi of S chi by the following formula. It is pi over q to the power minus S plus delta over 2, gamma of S plus delta over 2, L S chi. Then psi of S chi is an q is greater than 1, of course, is an entire function. And we have the following functional equation. Psi of 1 minus s chi bar is equal to I to the power delta square root of q divided by tau of chi, psi of s chi. So it turns out that you can write down an analog of the functional equation for the Riemann zeta function, but for L functions. And first of all, Q appears, of course, and second of all, for even and odd characters, you get different functional equations.
Okay, is the statement of this theorem clear?
Now, to prove this theorem, we need to establish a very important lemma. So, first of all, let me take a shortcut here. I am going to prove this only for odd characters, because for even characters, the proof is way too similar to the proof of Riemann zeta function.
Okay, so let me avoid the most similar part and tell you about the most different part. Let us formulate lemma 2. Lemma 2 is something about analogs of our theta series, but with Dirichlet character. Let chi be primitive modulo q. Define the following two functions. Theta of x chi will be equal to the sum over all n integers chi of n e to the power minus pi n squared x over q. This is the same as our theta function, which we used to prove functional equation for a Riemann zeta function, but with q and with chi, right? And also let us define theta 1 of x chi, which is sum over all n chi of n e to the power minus pi n squared x over q. This is a little bit different. Here you still get q in the exponent, but you also get n chi of n. Of course, if your chi is odd, then this thing is 0. And if chi is even, then this thing is 0, due to the fact that your exponent is even. Okay, so what is the statement of lemma? Then we have the following. Tau of chi bar multiplied by theta of x chi is equal to square root of q over x, theta of 1 over x chi bar, and tau of chi bar, theta 1 of x chi is equal to I square root of q over x cubed, theta 1 of 1 over x chi bar. So the first function transforms exactly like the theta function, but you get Gauss sum and square root of q. And the second also transforms similarly, but you get you get Gauss sum, you get q, also you get x cubed and I. So it is very similar, but it's different. Okay, so once again, let us prove it only for odd characters. So for odd theta function, theta 1, and for even theta function, this will be an exercise. So proof by Poisson summation. We know the following formula, that the sum over all n integers e to the power minus pi n squared, sorry, not n squared, n plus alpha squared multiplied by t is equal to 1 over square root of t, sum over all m integers, e to the power minus pi m squared over t plus 2 pi I m alpha. So this is an application of Poisson summation formula for this function of variable m, right? We already know the Fourier transform of this function. It differs from the Fourier transform of the function without alpha by the additional factor of 2 pi I m alpha. Correct? Now, what do we do next? Let us take a derivative of this identity with respect to alpha. D over d alpha
will get you what? Well, this is going to get you minus pi, minus 2 pi even, sum over, one more factor, minus 2 pi t, sum over all n in Z, n plus alpha, e to the power minus pi, n plus alpha squared t, right? And this is going to be equal to 1 over square root of t, sum over all m. Here you get 2 pi I m, 2 pi I m, e to the power minus pi m squared over t, plus 2 pi I m alpha.
And I would like to prove this identity. So let us start with the definition of theta 1. So once again, here you can of course cancel out 2 pi and minus, so that you get no 2 pi here, you get I, and you also get additional t in the denominator, right? Now, theta 1 of x chi is equal to, it is equal to the sum over all n and chi of n, e to the power minus pi n squared x over q. And then we are going to subdivide our sum into sums over residue classes. So if n is in some fixed residue class modulo q, then you get the same value of chi of n. So this will be equal to the sum over all what? Maybe all k from 0 to q minus 1. Then you get chi of k, and then you get the inner sum. Sum over all, say, once again, n. This is a different n here.
Может, до m обзовем?
What?
M. Как Михаил.
It's not very good, but okay. So m, then you get what? So your n should be congruent to k modulo q. So it is equal to mq plus k. mq plus k. Then you get e to the power minus pi x mq plus k squared divided by q. Correct? So this is equal to the following. This is the sum of all k mod q chi of k. Then you have, well, let us divide by q. We are going to get q outside, and then you get sum over all m, m plus k over q multiplied by. Here you should also divide by q. Then you get q outside of your square. You get q squared, and then divided by q. Then you get e to the power minus pi xq multiplied by m plus k over q squared. Now this sum, this inner sum, is very similar to what we get here, right? So this is the same sum, but your t is equal to xq, and your alpha is equal to k over q, right? Is it just completely the same? So let us transform it. Then we have sum over k from 0 to q minus 1, chi of k multiplied by q, and then you get I divided by xq to the power 3 over 2. And then you have this strange sum. So you get sum over all m, sum over all m. Yeah, this is the problem, because let us transform it into sum of L. Sum over all L.
А внизу там x.
xq в степени 3 вторых, как здесь. L e to the power minus pi L squared over xq, and plus 2 pi I kl over q. Right? Okay, now we need to continue the transformations. So this should now be equal to the sum over all L and then sum over K inside of it, yeah? So this is equal to I over xq to the power 3/2 multiplied by the sum over all L, e to the power minus pi L squared over xq, and then you have the inner sum. You also have q here, multiplied by the sum over all k from 0 to q minus 1, chi of k, e to the power 2 pi I kl over q. Can someone tell me what is the value of this sum?
Is it again the same argument than before? But
This is basically the Fourier transform, right? So this is equal to tau of chi multiplied by let me check if I wrote everything correctly. Yeah, probably. We will check it.
Хи с крышкой.
for you
С чертой.
you have minus in the.
Yeah, but this is
Почему с чертой-то?
Okay, go.
because you can change k to k divided by L, and then you get chi of k over L, right? And then k of L to the power minus 1 is outside the sum. Linear change of variables. That's
Sure.
it. Once again, this is by change. K goes to k L star. Okay, so what do we get here? We get I over xq to the power 3/2 multiplied by q multiplied by the sum over all L, chi bar of L multiplied by L multiplied by e to the power minus pi L squared over xq and multiplied by tau of chi. Right? So our statement now becomes that theta 1 of x chi is equal to I divided by x to the 3/2 square root of q, because it cancelled out. Oh no, sorry, square root of q should be, square root of q should be, of course, in the denominator. Square root of q, then you have tau of chi, and then you have theta 1 of 1 over x and chi bar, right?
А А можно переход пояснить, пожалуйста?
Который?
Еще раз. Вот сейчас.
Take all the
Сейчас,
outside.
все, сейчас. Да, все понятно, хорошо, да.
And the only thing you need to check now is that this factor will correctly transform into this, right? And this is basically obvious. So should we get maybe minus somewhere? No. Is this plus? It's plus. It's plus. Everything is fine. Okay, everything is fine then.
Кажется, мы ничего не должны были потерять.
Вроде не должны.
Сейчас, хотя стоп.
Хорошо, то есть получилось...
Не, у нас же получилось...
So we get the following. We get that tau of chi bar theta 1 of x chi is equal to...
Мы, кажется, без тета от хи с крышкой. Не с крышкой, с чертой делали.
Как это?
У нас, смотрите, вот мы начали с тета 1, да? Начали его преобразовывать, получили и тета тау от хи делить на x в степени 3 вторых на корень из q. И умножить на тета 1 с вот этой вот ужастью. То есть там как раз, когда мы поделим, у нас справа останется тета 1 от 1 делить на x. Сейчас.
So we get this, right?
Да, нам нужно по-хорошему получить корень из q делить на x в степени 3 вторых.
It's fine because absolute value of tau of chi is equal to square root of q.
И дальше...
So tau of chi multiplied by tau of chi conjugate is equal to q.
Сейчас.
Но
у нас...
but maybe I forgot some signs somewhere.
Сейчас. Вот такой вопрос тогда, почему у нас тау от хи на тау от хи с черточкой будет равно... Короче, почему у нас тау... То есть, почему у нас тау от хи сопряженного...
Мне кажется, что я где-то знак потерял один, извините. I think I lost some signs somewhere. Let me check for lost signs. Just in case. So I divided by... of course, that's insane. I divided I by minus 1 and I got I instead of minus I, sorry. So here you should get minus and then here you should also get minus, and here you should get minus, and here you also get minus, and so on. Everywhere where you get I, you should get minus I. But it's okay, because, well, you have this formula.
Сейчас, еще раз, у нас что произошло, где мы поправили знак?
I forgot the I here, because I divided I by minus 1 and somehow got still I, right? It's okay.
Сейчас.
Oh my god, we have like negative amount of time once again.
Так, получается, у всего этого счастья поменяется знак.
Minus I here, so we get minus I here. This is the first time we used this formula. And then you get minus everywhere, and then you get minus I multiplied by tau of chi bar. But tau of chi and everything bar is equal to sum over all k from 1 to plus infinity. Oh, sorry. Why plus infinity? Of course not. this should be q minus 1. Then you get chi of k bar, because you need to apply your bar to your sum. And then you get e to the minus 2 pi I k over q. And then it was plus, and then it became minus. So this will be minus tau of chi bar, because our character is odd. So this construction here in the numerator is actually equal to q. So this is equal to I multiplied by q. And then your square root of q cancels out, and you get the desired formula. Okay? And let me conclude the proof for odd characters. For even characters, this is an exercise.
Еще раз, у нас получается
Tau of chi multiplied by tau of chi bar is equal to minus q because of this formula. And so you get minus I multiplied by minus q, which is I multiplied by q. Everything is fine. Luckily, everything is fine. Okay, so what I would like to state now is that pi over q to the power minus s plus 1 over 2, gamma of s plus 1 over 2, L s chi for odd chi is equal to 1/2 integral from 0 to plus infinity x to the power s over 2 minus 1/2 theta 1 of x chi dx. Okay? This statement follows from the fact that integral from 0 to plus infinity x to the power half of s minus half multiplied by e to the power minus pi n squared x over q dx is equal to what? Well, it is equal to pi over q to the power s plus 1 over 2. Then you get n to the power minus s minus 1, and then you get gamma of s plus 1 over 2. Okay? And then you multiply it by n chi of n and sum over all integer values of n. So you get, this should be an absolute value, sorry. So you sum over all, you multiply it by n chi of n, then you sum over all integer values of n, and you get two L functions. So to cancel out this two, you should get 1/2 here. Okay?
Можно
So we have this integral.
Так,
Вот этот интеграл получается линейной заменой просто.
Хорошо, в это можно еще поверить.
Now integral from 0 to plus infinity x to the power half of s minus 1/2 n chi of n.
Еще раз у нас
Let us integrate the summand in our theta function. Then we get this integral, but multiply it by n chi of n. This is equal to the same, pi over q, minus s plus 1 over 2, gamma s plus 1 over 2, and then you get this value is the same as the value at absolute value of n, so you get absolute value of n to the power minus s chi of absolute value of n. And then you sum it over all integers. For 0 you get 0, and for negative integers you get the same as for the positive integers. And so your L function will appear 2 times when you sum over all n. Okay? Теперь работает?
я просто что-то как-то запутался в происходящем. Еще раз, у нас что? Во-первых, замена самая первая не очень понятна. То есть откуда у нас первое равенство взялось, самое первое на доске?
Это доказательство этого равенства.
Хорошо.
the first identity is from the linear change of variables. The second is just the first multiplied by n chi of n.
Мы, вот первая, ну, вторая строка на доске, на всей, то есть... мы,
This is
получается,
linear change of variables, nothing more, nothing less.
Сейчас.
Eliminate this factor. That's it.
Сейчас, я, видимо, запутался, не очень понимаю, как мы так заменяли. Вот.
X is equal to qy over pi n squared. That's it. Then you get e to the power minus y, right? Okay, so let me write down the formula we are going to get. So this thing is psi of s chi. Then if we multiply it by tau of chi bar, we are going to get 1/2 integral from 0 to plus infinity x to the power half of s minus half tau of chi bar theta 1 of x theta dx, and this can be transformed by our lemma 3, right? So this is equal to 1/2 integral from 0 to plus infinity x to the power half of s minus half. Now you get I square root of q divided by x to the power 3/2. Then you get theta 1 of 1 over x chi bar dx. And then you need to make a change of variables. Is x is equal to 1 over z. And from this change of variables, you are going to get the following. So this is equal to 1/2 integral from 0 to plus infinity z to the power half minus half of s I square root of q z to the power 3/2 theta 1 of z chi bar dz over z. Right? This is basically the same integral. Basically. So this is equal to I square root of q over 2 integral from 0 to plus infinity, and then you get z to the power half, so you get z to the power 1 minus half of s theta 1 of z chi bar dz. And this is the same integral as here, but for chi replaced by chi bar and s replaced by 1 minus s. So same integral, s replaced by 1 minus s, and chi is replaced by chi bar. And here is where I must stop, because we already are 10 minutes over time. So thank you for your attention, and please, if you have like one last question, you can ask it. If not, then I stop everything. If not, then I...
Okay, we proceed with problem 1. So what is product of tau of chi multiplied by tau of psi? It's sum over
КФН psi of m x of...
yes, chi of a psi of... No, let it be in psi...
Oops. It's okay.
Psi of b and exponent of the pi q over q of n of a plus b. Yes, a plus b. And what is tau of psi multiplied by g? What is this?
Wait, maybe it's better to start with this identity and then transform it somewhat, not? No?
Let us just compare two parts. I think it's
Okay.
the same. Here it will be
Interesting.
sum from m from 0 up to q minus 1, chi of m,
Psi of
psi of m, q of m, and multiplied by
It's okay.
uh-huh,
You can just.
sum over x plus y is 1, x psi over y.
Uh-huh.
And as you see, we can x and y
Y.
Okay, y multiply by m. Yes. And when
Сейчас, извиняюсь, тогда вот вопрос. У нас, во-первых, в определении суммы Якоби у нас то есть у нас, получается, здесь x плюс y целые должны быть, да?
единица. Нет.
X и y целые, так?
Нет, это z по
От
q
0
z.
до q минус 1 они
Это
бегают.
z по q z элементы. В смысле, это по...
А,
это
Да,
с модула.
Так не бывает. Либо модуло убрать, либо
Ага.
написать модуло q.
Короче, x и y элементы.
Да, то есть мы по всем таким парам проходимся.
Что сумма 1, да.
Ага.
By the way, in some sense, Gauss sum is an analog of gamma function, and Jacobi sum is an analog of beta function.
And so I say that we can
Yeah.
change x and y to mx, my.
So just multiply the sums,
yes,
and you get the following.
and so if the sum of these two is 1, then the sum of these two is m. And this is bijection if m is relatively prime to q. Yes.
This is bijection of what?
Of pair of x and y such that they sum are 1 and x and y if they sum is m.
Yeah, non-zero.
Сейчас. То есть мы берем m взаимно простые с...
Да, потому что не взаимно простые здесь 0. If they are not relative prime, this would be 0. So this is equal to what? Maybe you can tell now. Sum of x plus y is so it should be relatively prime to q, yes? And then we have psi of x, psi y, q of x plus y, x plus y.
Is this transformation clear?
Because here m is so here we change x and y by mx and my.
So just multiply everything together, you get chi of mx, psi of mx, eq of m, right?
Of my.
Mx and psi of my, yeah. And if the sum, so m, is coprime to q,
Okay,
then this is a bijection.
this is sum over m
Окей.
and okay.
Еще раз.
Окей.
Что у нас произошло? То есть, получается, мы как сделали? Мы домножили оба. Их сумма, очевидно, стала все еще взаимно проста.
Сейчас, вот давайте перепишем это как двойную сумму.
Yeah, let me rewrite it as follows. If m is coprime to q, yes, otherwise this is 0. And if it's coprime, then this will be x
Psi, not chi.
psi, yes, psi y q of x plus y. Okay?
Yeah.
I changed x y by mx and y. Is this?
Еще раз, у нас получается есть внешняя сумма, которая...
Не, это просто две суммы, мы их перемножаем.
Так у нас... да, хорошо. Мы перемножаем их. А куда у нас делится?
Получается mx и my, да, внутри характеров.
А, все. То есть... и дальше, почему у нас все легально остается?
В чем проблема?
У нас как раз таки с mx и... потому что мы...
Fix m. Multiply the summand on the left by the thing on the right.
Да.
You get chi of mx, psi of my, eq of m. Then denote mx by x, my by y. Then m is x plus y, and you get chi of x, psi of y, right?
Концовку, к сожалению, на английском очень тяжело.
У нас есть
Сейчас.
chi от mx,
Да, есть,
chi
да.
от my,
Да.
и eq от
Да.
m.
Да. Вот.
Теперь обозначим mx через x, my через y. Линейная замена переменных,
Я
как
понял.
обычно.
Короче, у нас сумма аргументов была 1, стал m.
Да. Не, я просто не понял вот этого момента замены, как он
Да,
произошел.
и я тоже не люблю, когда mx заменяют на x.
Да,
Какой-то
да.
разовый тоже.
А.
Язык как бы, но все нормально.
Окей.
X штрих плюс y штрих тогда.
This is actually better.
Okay.
Because
And now we see that
Искусство развлечения.
with sums are similar, but they are different by what? If x plus y is not coprime to q, and if q is prime, it means that the sum is 0. So they are different by such term. Sum over, I'll write it over x.
This way. You should write that the difference of these two things is equal to.
Okay, this is A, this is B, and A minus B is equal to what? Sum over x, y will be minus x, and he will get chi of x, psi of minus x,
And exponent of 0.
and exponent of 0 is 1. And why such sum is 0?
Сейчас.
Преобразование понятно?
Сейчас мы вычли из одного другое. И почему у нас...
So this is the same sum, but the only difference is that we require the sum to be coprime to Q. Right? So the difference is the same sum, but the sum is not coprime to Q. There it is. If Q is prime, that being not coprime to Q is the same as the sum is 0.
X plus y is 0, and it means this y is minus x.
Все.
Okay, and y is 0. If and we know that chi psi is not principal.
Well, it's the same as we can get -1 out of the
Yes, we can.
side, and so we have some constant multiplied by the sum of everything of non-principal
Uh-huh. And the sum.
character.
Yes.
And I think we had a theorem about this on the left.
Сейчас, и дальше получаем, что как раз вот эта вот сумма, она у нас занулится.
Конечно.
Спасибо.
Okay, next, we first prove the same if the product is primitive, but let's keep this problem because we have other things to do.
This will be an exercise. About if Q is not prime, then what can we do?
Problem 2 is to prove that if P is not 7, then every element is the sum of 2 cubes modulo 7.
Yes, this problem can be solved by several different.
Yes, actually we'll see that there are, for large prime, there are many ways to represent it as the sum of 2 cubes.
Существует также элементарное решение, совершенно элементарное, но оно немножко отвратительное.
Okay, first, prove that there is a character epsilon modulo prime. Our prime is 1 modulo 3.
Сейчас, а B мы как сказали, что...
Вы ignored.
Ага.
And prove that there is such character that 1 plus epsilon of A plus square of epsilon of A.
No. First thing to prove is that there is a character of order 3.
Order 3.
What is order 3?
This means that it is of order 3 as an element of the corresponding group of characters.
It means that
it
it's
is
to
not
power
equal.
3 is principal, but it is not principal. Okay, sure.
Cubed, not squared.
Cubed, yes.
Сейчас. Еще раз, порядок третьего порядка подразумевает, что просто в кубе любой элемент единица.
No, non-zero element is 1, but there is element which is not 1. But epsilon is not principal. So, and when, of course, we have that such sum is free if A is cubic residue.
Non-zero.
0. 1 if A is 0 modulo P, and 0 otherwise.
So basically, this 1 plus epsilon squared is the number of solutions to the congruence A is congruent to x cubed. So it is the number of cube roots. So how do we prove that there is a character of order 3?
What you just said is
This
number
1
of
plus epsilon,
solutions to
1 plus epsilon squared is the number of solutions to the congruence A is congruent to x cubed.
Why do we have such character? I think we can construct it by right. First question: do you know if we have Z over D multiplicative group? It's of
What
course
is the structure?
what is of course it's abelian group, and we know the structure of all abelian groups. What's this abelian group?
is it cyc?
Yes, it's cyclic, and of order
Like P modulo.
is p minus 1. So
Please don't write it like this. This isomorphism is not canonical.
like this.
Uh-huh.
So there is an element, primitive, yes,
Primitive root.
primitive root. That is zeta. So zeta is a primitive root, and to define any character, we need to define it on zeta. And then all other elements are powers of zeta. And what it should be? Epsilon of zeta.
So take any primitive root module P and let us define our character on this primitive root and then extend it by multiplicativity.
Actually, every character on modulo prime is we can define in such way.
So what is the value of this?
Yes, what should be the value of this?
I think it's 3.
3.
Мне кажется, Dell должно быть.
Character should be, value should be one
Root
module.
of unity.
Root of which root?
Well, just answer.
Все.
Character should be multiplicative.
Сейчас. Ну, значит, да.
We know that epsilon of zeta cube. Okay.
Ну да, какой-то примитивный корень.
Yes, yes.
Единица.
Корень какой степени из единицы?
3.
Какой-нибудь корень третьей степени из единицы знаете?
Но есть степени плюс-минус 2.
No, epsilon of zeta is not a third root of unity because. Maybe yes, yes. You want it to be. Okay, let us write it in such.
Cube root of 1.
Cube root
Because we
of
want it to be 0, right? 1 plus epsilon of
we want
we want it to be 0, right?
We want what to be 0?
1 plus epsilon of psi plus epsilon squared.
we want that cube of this is 1. So there is only one way, two ways actually, yes, conjugate, to define it like that. And third way is a principal character. Okay, and then epsilon of zeta to the power n is this root.
Please name it like denoted by omega, please. Cube root of 1 is equal to omega.
Okay, omega.
Because
Okay,
it's
omega to the power n.
very trying to see cube root of 3 to the power, cube root of 1 to the power n.
Yes.
Right?
And of course it is 1 on cubes. And how to prove such formula? If a is 0,
If a is 0, then
Then it's 0.
no, when it's 1 because
Then it's 1 obviously.
1 plus 0 plus 0. That's it.
When it's
when it's cube, when it's
cubic non-zero residue, then it's obviously 3 because
It's 1 plus 1 plus 1.
yes.
yes. And 0 if not a cubic residue.
Yes. Стоп. А у нас да, понятно почему, да. No,
Right.
and if it's not a cubic residue,
Yes,
then
some of them
then this is
should be omega and
omega
square.
Omega square. Yeah.
Yes.
And omega plus omega square is of course equal to
-1.
Sum is 0, yes. Okay, and now we want to deduce if number.
So there are actually two characters. This one.
Epsilon and epsilon square.
Нет, там речь про то, что просто в целом у нас одно из этих двух чисел, эпсилон и эпсилон квадрата, будет омега, и второе омега квадрата.
И я к тому, что можно даже два таких характера определить.
Ну, вот эпсилон и эпсилон квадрат, это два такие, они есть. Окей. M is given, it's a let it be non-zero because for 0 it's 0 cube plus 0 cube. M is non-zero, and when we want to prove that it is representable as x cube plus y cube. Do you have any ideas?
This is B, right?
Yes, this is big. How? Use problem A. This. Use this. We have actually we have characteristic function for cubes.
Может, мы возьмем один характер такой, а второй какой-нибудь еще?
No. We have a characteristic function.
Или просто возьмем вот этот вот с собой и запихнем в Якобе?
То есть как?
Якоби сумма его с ним же будет, получается,
Не,
хрень какой-то.
Здесь что-то не то.
We need an idea how
Причем здесь сумма кубов?
yes.
Ну, это значит, что у нас минус единица куб, кажется. Нет.
We want to represent M as A plus B, such way A is cubic residue, so this is free of 1, and B is also, this is free of 1.
So we want representations of M of the form A plus B, such that neither 1 plus epsilon of A plus epsilon squared of A is 0, nor 1 plus epsilon of B plus epsilon squared of B is 0, right?
Mm-hmm.
If we have at least one such representation, then everything is nice. So how do we proceed?
Not just 0, it could be also.
Yeah, if both factors are 0, then we fail. If at least one of these factors is 0 always, then we failed to prove that it is sum of two cubes, right? So what do we need?
Сейчас. Надо же...
То есть еще раз, идея.
Вот не очень понятно, в чем проблема того, что один из кубов нулевым будет.
Никакой проблемы, вот у вас там единичка.
Ну.
То есть еще раз, в чем идея? Можно, да?
У нас есть, мы смотрим на все решения. Look at all the solutions to M equals A plus B. Then over all such solutions, let us consider this thing and also this thing. Whoops. If they are always, once again incorrect. If they are always 0, if at least one of them is always 0, then we have no solutions.
Otherwise we have a solution.
So what do we do now?
Otherwise we have a solution.
Otherwise we have a solution, of course. Because when we know that A and B are 0 or cubic residues, and so they are cubes.
So you have two functions. You have one function, f of a.
Well, multiply them.
Multiply them, and then what?
Then use the multiplicativity.
Yeah, you multiply it, and then what do you do?
Получается мультипликативность характеров.
Не, подожди. Пока у нас есть произведение двух сумм.
Yes, and this is not 0 if and only if A and B are both cubes.
So what do we do next with this product?
We want to say that it's non-zero.
Yes, it's not 0 if A and B are cubes.
We can open the brackets.
No, but what is A and B here? It's us, this also.
It's...
And we want to connect it with M. M should be A plus B.
Предлагаете по формуле сокращенного умножения.
Подождите.
Может мы тогда перепишем B как M минус A?
Давайте лучше напишем сумму. Наконец уже.
Ну у нас...
Вот. Вот если эта сумма 0, тогда у нас проблемы. А если не 0, то никаких проблем нет.
Actually, this function counts the number of solutions.
Mm.
X cube plus I cube is M. Okay, and now we can compute this function. We have 9 sums, 6 sums, but okay, let's first open brackets. 1 will give what?
M.
Yes, M. No M, but P. Yes, because
There are P solutions.
this is
yeah.
So there are P solutions, and one with, for example, epsilon. Epsilon.
We have 9 summons here, right? Corresponding
yes,
to 1 multiplied by 1, 1 multiplied by epsilon.
What is
multiplied
1 multiplied by epsilon? Such sum.
It must be 0.
Yes, 0. So 1 with everything else is 0, because it's sum over
See.
all residues of values of character. And okay.
So in our sum of 9 summons, we have 4 zeros, right?
Yes, 4
One
zeros.
is epsilon with
and
one
now we
is
have
epsilon squared.
Now we have such sum. So what it will be? I think we can write it in terms of Jacobi.
Сейчас кажется...
We have 1 summon which is P, 4 summons which are 0, and we have how many? 4 summons left, right? So let's look at these summons. What do we get? We have epsilon, 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 epsilon squared, epsilon squared, epsilon, and epsilon squared, epsilon squared, right?
Yeah. What will be sum of epsilon of A? Epsilon of B. Example. A plus B is M. Think we can. M is not 0.
If m is 0, then 0
Well,
always is
yes,
zero,
we
right?
already said that it's obvious. Now M is not 0, so it will be epsilon square of M conjugate multiplied by sum A plus B is 1
Why conjugate? Where do we get conjugates?
to the power minus 1, I think.
No.
Uh,
A is equal
yes,
to...
not conjugate. And this is Jacobi's sum, yes?
Еще раз.
C and D, please. No A and B. Change the variables.
Мы просто делим на M, да?
It's A and B from Y.
Okay. I think everybody...
Jacobi of epsilon.
Right?
Yes, and what's the absolute value of this expression?
We should use problem 1.
Yes. You know that Jacobi is expressed in terms of Gauss sum, and for Gauss sum, you know its absolute value. Absolute value is what?
From the left.
You should know that.
Something like square root
Square root of
of
Q, yes.
Of K in this
Of
case.
P, yes. So this will be what? For Jacobi sum. Absolute value?
also need the epsilon square root of m. It's 1, so just square root of m.
Yes, square root of p, because you multiply two Gauss sum and then divide by.
Сейчас. Еще раз, можно вот объяснить, что произошло сейчас?
Мы говорим, что это по модулю равно корень из p. Потому что мы знаем, что для Гаусса суммы у нас корень из p по модулю, а это две Гаусса суммы из произведения разделить на третью. And if epsilon square is square, we get the same. And now we have only two terms. In this case, the product is a principal character, so we need to compute Jacobi sum in case that the product is principal.
Мы же получим только по модулю значение.
Ну хорошо, оценим просто.
То есть нам достаточно просто оценить.
Сейчас увидим.
Sum
Ладно.
epsilon
Ага, я понял,
p,
что.
epsilon square of p, a plus b is 1.
Петя, можно попросить?
Да.
Можно я более внятно напишу, чтобы это больше проблем не было? Значит, еще раз. У нас есть сумма а плюс b равно m. 1 плюс эпсилон от а
Ой, я m забыл, да? Там m, ну хорошо.
плюс эпсилон квадрат от а плюс 1 плюс эпсилон от b плюс эпсилон квадрат от b. Правильно? Давайте скобки раскроем. Давайте вот я просто напишу нормально, да? Что здесь происходит. Я извиняюсь, что я прям так ругаюсь, но тем не менее. 1 плюс эпсилон от а плюс эпсилон квадрат от а плюс эпсилон от b плюс эпсилон от а эпсилон квадрат от b плюс
Эпсилон b в квадрате.
плюс сейчас что-то я не то делаю, да?
Эпсилон b в квадрате.
Не, вот так надо делать. Значит, эпсилон от а эпсилон от b плюс эпсилон от эпсилон квадрат от а эпсилон от b плюс эпсилон квадрат от b плюс эпсилон квадрат от b эпсилон от а плюс эпсилон квадрат от а эпсилон квадрат от b. Правильно? Это я скобки раскрыл. Согласны?
Да. У нас вот единица даст p, одиночные дадут нам нули.
Вот это даст p, это даст 0, это даст 0, это тоже даст 0,
И еще там.
и это даст 0. Да? Значит, наша сумма равна p. Дальше у нас есть вот эта штука, да?
Ну да, по
Это
модулю
что?
она даст нам корень из p.
Давайте, я просто напишу ее. Йод, эпсилон, эпсилон. Дальше есть еще штука с эпсилон квадратом, да?
Да.
То же
То же самое для эпсилон квадрата.
Эпсилон от m. Йод, эпсилон квадрат, да? И что еще? И еще две суммы осталось. Вот
Они
это
одинаковые.
И вот это. Они одинаковые, правда?
Ну да.
Да.
2.
2 умножить на сумму по а плюс b равно m.
Опять можно... да.
Эпсилон от а, эпсилон квадрат от b. Теперь нужно выяснить, что вот с этой суммой последней делать, правильно? Все остальное мы более-менее поняли.
Да, и мы можем вынести m и написать здесь единичку.
Все понимают, почему можно вынести m и написать единичку?
Don't we require that m is co-prime with something when we do it?
When we do it, yes, but
But
everything is
if-
co-prime if it's not zero.
If m is not co-prime, then m is 0, and 0 is obviously sum of two cubes.
So finally we need to compute such sum.
Сейчас. Еще раз у нас. Мы почему вынесли m спокойно?
Что там выносится эпсилон в третий, да?
Да, хорошо.
We need to compute such sum. And we know that epsilon square is epsilon to the power minus 1. Yes? So this is sum a plus b is 1. Epsilon of a over b. Yes?
Yeah, but we also need to require
If
that
b is not 0, if it's 0,
Then we get 0.
Yes, we get 0.
That's because epsilon squared is the same as epsilon to the power of minus 1.
Yes.
Yeah.
And what's this? It's sum of, let it be sum of p from 1 up to p minus 1.
P minus P,
P minus 1, yes.
excluding.
Excluding 0. B is not 0.
Wait. B should also. It's okay. Sorry.
1 minus b over b.
Right.
It's
So when
1
B.
over b minus 1. If b runs from 1 up to p minus 1, this expression runs for all residues except what? Except one residual, which one?
B equals 0.
B is not equal to 0.
So B runs from 1 to P minus 1. So 1 over B minus 1 runs over what?
B minus 1.
Yes. It runs over all residues except minus 1.
Okay, the B.
Because 1 over b is a bijunction.
So this is a complete sum minus value at minus 1.
So it's, yes, minus value, minus 1. And this has modular absolute value 1.
No, epsilon of minus 1 is just equal to 1.
Сейчас, не может быть.
Minus 1 is a cube.
Yes, it's always okay. It's 1.
It's minus 1.
Yes.
Because it's minus epsilon.
Yes, it's minus 1.
Uh-huh.
So this is minus 2.
Yeah, so we get.
So
two
our
minus
sum,
2.
yes, our sum is like that, and how we can give lower bound for such sum?
It's pi minus 2
Our sum S of m, let it be.
minus 2 square roots of pi.
Yes, it's
P minus
p minus 2 square roots of pi minus 2.
P.
Minus 2.
Mhm.
P.
And then,
Yes, S of m. And
And we want this to be positive.
and this should be positive for any p other than 7.
it should be when x is bigger than 2 square root of x minus 2. It's quadratic polynomial.
Square root of x minus 1.
Ну, просто x минус 1 больше, чем...
Square root of x minus 1 is greater than 3.
And this is I computed it.
Petya, this is incorrect.
We should compare it with
This
sum.
is incorrect.
Что не так?
There are two.
Here we should
Ну,
write
у
that
нас-
x bigger than 0.
No.
No.
Also, if
Okay,
if x is less than.
Okay. Just let me write like that.
Okay. So if your prime is greater than 7, then everything is okay. If it is less than 7, then it is not congruent to 1 modulo 3. So everything is a cube, not only sum of the cubes, right?
And for 7, not everything is a cube.
Там для любого x это будет.
What?
Либо я не умею считать.
Что?
Не умеете.
Ну, давай, хорошо,
Если
давайте...
так, неправда.
Вот хорошо, для любого положения, неотрицательного.
Для семерки неправда, говорю же.
Сейчас.
О чем разговор?
5 минус 2 корня из 7.
Где я не умею считать? Так у нас же там получается слева будет x.
5 минус 2
5
корня
минус
из
2
7.
корня.
Сейчас. У нас, смотрите, у нас же, еще раз, слева, если мы все влево перенесем, получится x минус, корень из x минус 1 квадрат плюс 1. Больше либо равно нуля.
Не плюс 1, минус 3.
Не-не, давай.
Потому что вот это неравенство опять написано неправильно, я очень извиняюсь. Плюс.
Плюс. Хорошо.
А! Все, тогда да.
Now,
And this is actually a generalizable thing. If you want to prove that that modulo p, any number is the sum of n powers, you can do the same, basically.
now problem.
Сейчас еще раз у нас. Еще раз, у нас получается как? Что для любого простого x, кроме семерки, это все хорошо.
Да, до семерки.
Для семерки все плохо, потому что
Да.
там кубы это 0 и плюс-минус 1.
А,
Now, problem free, maybe we will return to problem free, where you prove that one of chi is not zero, if chi is real non-principal character, and from lecture you know that it's the only case where this it's harder. If chi is not real, is complex, then it's easy problem. And here the proof is that we define function chi degree product with 1 and
Do you have evolution?
convolution, yes, with 1, and after that we have such 3b, such formula. To prove that we use Dirichlet hyperbola method, we can use because if we have such convolution,
Wait.
я хочу ее пропустить.
First things first.
Я хотел пропустить.
Почему?
Потому что другой место.
Окей.
Я просто хотел сказать, что мы делаем. Maybe we'll return. And so you, using Dirichlet hyperbola method, you can prove such formula, and then you note that left part is not big of 1, it's bigger. And that's why L should not be 0. That's the idea. But let's problem 4. In problem 4, we want to find Gauss sum. If chi is quadratic character. So let
сейчас, еще раз у нас.
Вы
Третья
пробуете.
задача сначала, что у нас происходит?
ну, третья сказала идею, значит, что мы доказываем, что L равно нулю единице.
У нас настолько мало времени.
Да?
У нас полчаса еще.
Ну там еще отлично, значит, что.
Я просто говорю, что мы хотим доказать, что
We are going
L...
to skip this problem.
Да, мы skip this problem.
Сейчас.
Maybe after seminar you can ask them.
Да понять бы условия выходные еще раз. У нас получается.
We skip it.
Честно, характер.
Let's proceed with problem 4.
А, мы четвертую. Все.
Yes, problem 4.
Все. Я просто смотрю третью, а четвертую не видно просто в этом все.
P is prime. Yes, and we have quadratic character. I of n is just genre symbol. And the P. Okay, and we have Gauss sum. Gauss sum. It's tau here. Sum chi of n.
А и правда ли, что там что в этом условие опечатка, да?
Да, там n, а не. Okay, and we want to compute such sum. We know that. What do we know? We know that g square is that it is p if p is 1 modulo 4. And we know that it is I. Сейчас. получается, да?
Что?
Сейчас, вот g
Минус
square.
p.
Минус p, а здесь i.
Нет, там p, там минус p.
А, все, хорошо.
Лонг.
Минус p.
Нет, тут плюс, а там минус.
Хорошо. Yes, but we don't. So we know that in this case, j is plus minus p, and in this case it is plus minus ip, but we don't know what sign is. And we want to compute it.
Сейчас, а там сумма в G у нас от единицы до чего? Еще раз до Q?
Да, p минус 1, да. Сумма по всем вычетам. Okay, and but this can be G can be written in such a way. It's sum over squares. Q of n squared. N modulo Q. And from 0 up to Q minus 1. Do you see why this is true?
Or it's going to be 0 for all n.
Yes, because this is 1 or minus 1 if n is so let us write it as sum n square minus sum n is this is quadratic residue, it is non-residue. And we can add plus sum over all n from 0 up to q minus 1 q of n because this is 0. Yes, and you see that we have eq of 0, which is 1, plus such double sum. Yes, and
Еще раз, у нас как получилось? У нас мы из квадратов вычли не квадраты и прибавили...
Там не только не квадрат. Ну,
Да. И прибавили что? Просто всю сумму?
ну, сумму по всем n, да, и она 0. Экспоненты 0. 1 плюс омега квадрат был 0. Здесь то же самое с экспонентой.
Если честно, лучше не стало.
Окей.
Сейчас.
N from 0 up to q minus 1, it's exponent of 2 pi I n over q. And this is arithmetic progression. So this is exponent of 2 pi I q minus 1 over q, I think, not q minus 1, but q. Q over q minus the same at 0. Minus 1 divided by, this is 0, because у нас сумма по корням n-той степени из q-той степени из единицы, но она 0, конечно. Что, правильно?
Сейчас, еще раз. Я скорее не очень понимаю, зачем мы прибавляем сюда.
Ну, чтобы сказать, что вот это равно, вот это равно вот этому. Тогда вот это, if we add such sum, when sum over non-residual cancels, and this will be double sum.
А,
Plus, also plus 1. And with double sum, because every quadratic residue is written as a cube in two ways. N square and minus n square.
It's going to be double sum. Double the sum.
Yes, so this is equal to 1 plus sum n is quadratic residue EQ of n double sum. And this is exactly such expression. Okay, and how to compute this expression? First, do you remember Poisson summation formula? Let me remind you. Let me remind you. Let f be a function, and when we can construct such function, let it be f, big F of x is sum f of x plus n over integers. Yes? And if f is a nice function, so this is convergent, then big F is periodic. Do you agree? Yes. And when is big F is periodic, we can decompose it into Fourier series. And do you know when Fourier series converges to a value of function? There are some criterions. For example, if it's differentiable, then it converges. But continuity is not enough. But let f has be a function with compact support. So yes, and from this we will get, if you do it, you will get such formula that sum of f of n is equal to sum of it's Fourier transform. Yes. Let me remind you, f of x is integral from minus infinity to infinity, f of y, e of minus x y dy. Okay. It's if f is such function that at 0 its Fourier series converges to its value at 0, then we have such formula. Because this is the value of f at 0, and this is its Fourier series at 0. And if we have such sum from a up to b, f of n, we want to compute, okay? Somehow using this formula. So we can just take f to be a function which is from a up to b, it is our function f, yes? And otherwise it is 0. Okay, then such sum over all integers, it will be such sum, yes? And what it will be, big F. So we have such sum, yes? We assume small f is continuous, yes? When big F will be, it will be continuous everywhere except what? If a, bk, and b are integers.
In B plus F.
Yes, so f of x, it will be some function. Yes, it's from 0 to 1, it's periodic. But at 0 and 1, its values, here it will be, the values may be different. So it's continuous everywhere except the endpoints, yes? Because if we change x, then to the left, and so it will be difference f of b minus f of a. Okay, and you know if function is differentiable, but it has one point, разрыв какой-то. Of discontinuity, okay. When the Fourier series converges to what? To the middle, yes, to this middle point. You know, I think you know it's from the standard course. So here we should take not the sum, but sum prime. So it means that we take f of a over 2. And f of b also over 2. Okay? And then we can use such formula. So
Еще раз, что у нас произошло сейчас? Вот как мы решили...
ну, мы вот пишем f большую, вот я график как бы f большую
Да.
написал. У нее есть точка разрыва.
Да.
И ряд Фурье, вот, который справа, там, самый настоящий ряд Фурье для f большой, он
Да.
будет сходиться к середине этой точки. К середине значению, среднему значению между концами.
Почему?
Ну, потому что вот так все ряды Фурье.
Ладно, хорошо, верю.
Можно еще раз объяснить?
f от a пополам, f от b пополам, это у нас...
Это вот в этой сумме f от a будет со значением 1/2, чтобы вот в сумме получилось как раз вот среднее значение между точками разрыва. То есть нам надо сюда двинуть. И сюда. Okay, and when we have such, if small f is differentiable, then everything works, and we have such formula. And to be f of n prime is equal.
А что вот сумма, вот именно сам prime, что она делает?
Это что концы мы берем с коэффициентом 1/2, чтобы вот
Понял.
усреднить.
Понял. Спасибо.
This will be our usual formula sum over n Fourier transform. And what's this? It's sum over integers, integral, and this integral will be from a to b because it's support of our function f of x e of minus ix d I. Ой, sorry. Okay, and we want to compute sum of from n0 up to q minus 1 of e to the power 2 pi n square over q. Yes? And I suggest to use this formula because Fourier transform of this function is nice. What it will be. So what's our function f? F of x is what?
In problem what?
Yeah, here we want to. Yes, in problem 4. We want to compute such sum. Yes? This is exactly our job. Actually, from this point, we don't need that q is prime. Actually, q is a natural number. What's our function f? Small f here. Yes, f of x is e to the power 2 pi x squared over here. Yes. And what is a and b? A is 0 and b is what? Our function is q periodic. So we can take b to be q. Okay? Because when we have 1/2 at 0 and 1/2 at q. Actually, our function here will be it will be continuous. Окей?
Сейчас. У нас экспонент делить на...
Ну, вот это от 0 до P определяем, и f большое. Вроде тут.
Вопрос. У нас x квадрат делить на q в показателе степени.
Да, да, да.
Да.
Да. Yes, so this will be sum over integers. And now we just compute such interval from 0 to q. Exponent of 2 pi I x square over q minus nx, yes? dx. Oh, no, yes. Okay, now we should just compute such sum. How to compute it? First, let us change, so it will be integral from 0 to 1 of what?
We can just changing the variable.
First, I suggest to change the variable, so it will be integral from 0 up to 1. So x, we change it to qi, yes. And so I think what it will be.
First of all,
It will be quite good because
first of all, we get Q.
yeah, we get q out of in the experiments. Yeah.
And here 2 pi I
QX.
X squared minus n multiplied by q.
q x square minus n, yes?
Yes, I think.
dx.
NX, not N.
nx.
NX.
Yes, nx. Okay, now we have quadratic polynomial. Let's take it, сказать,
Complete the square.
complete the square, yes. So we should change variable, our variable. What it will be? Let's take
X
I.
minus.
x minus n over 2, yes?
Mhm.
Yes. And what it will be? Q sum over n in z integral from minus n over 2 up to 1 minus n over 2 of what? 2 pi I, here will be I square, yes? Q I square, and di, and also there will be what? A constant. I think exponent
Over 4.
2 pi I of what?
X squared over 4.
We know x because
N squared.
n squared over 4 over
With minus and also with Q, right?
minus n square.
Сейчас, там, я извиняюсь, а мы нигде не потеряли... Сейчас, еще раз. Можно попросить вас повторить переход вот к предпоследней строчке? Вот после того, как мы...
Вот к этой?
Да, вот к этому.
Ну, заменили интеграл от 0 до q, сделали там x равно q y, а y теперь от 0 до единицы. А вот оно q вывезли из d.
Ага. А вот замена то, что y равно x минус n пополам, это...
Ну, это замена, чтобы главную часть сделать. Потому что теперь y в квадрате равно квадрат минус xn, ну еще
Плюс m квадрат на 4.
плюс n квадрат на 4.
Полный квадрат.
Ну, полный квадрат.
Да, то есть
So it should be... Yes.
Что за вами не видно
А
почти?
что за экспонент?
Пишите.
Вот это вот такого вынес.
Minus, yes,
Да.
2 pi I
N
q n square over 4. And now this is a constant, which depends, of course it depends, it's not a constant, q, our, yes, it,
Q might be even, might be odd. N also might be even, might be odd.
За вами не видно просто.
If n is even, then this exponent is equal to 1.
yes, but q is prime.
Ага.
Okay, the claim is if n is even, then it is 1, and if it is odd, then it is ei to the power minus q, and here q is arbitrary and integer. Do you agree with this?
Me too.
N squared is congruent either to 0 or to 1 modulo 4. That's it. Yeah, then we sum separately over evens and odds and get the same integral.
Yes, yes, now we did sum separately. It's q, and then it is, let's sum over even n. And if we sum over even n, this is just integral over all real
Yeah,
numbers.
so these intervals, they glue together into the whole real line.
And you see this integral, if we write it over all real line, it converges very well, not like a principal value, but so if we
It
write...
just converges.
Ну, converges в смысле мы можем взять и справа и слева, то есть не главное значение.
Uh-huh.
Это понятно, да?
It just converges as an improper integral.
Yes. So this will be q multiplied by 1 plus I to the power minus q, and here will be such integral. Integral over real numbers e to the power 2 pi I q I square di. And what's this?
It's going to be the...
Now let's make the final change of variable. Q, we have q here. Let's take z square to be qi square. So z is square root of qi. Yes. So we will get square root of q, 1 plus I to the power minus q, multiplied by, now this will be an integral over 2 pi I square di. And this is an absolute constant. Okay? And it does not depend on q.
Wait, what is this q squared? What did we get? It's we made, okay.
Yeah.
Same.
And this is an absolute constant. And for example, we can take q equal to 1.
Uh-huh.
Q equal to 1, then
G
this
is
is
equal to
1. So we get 1 is equal to q.
1.
Q is 1, yes. 1 plus I minus q.
Minus 1.
Что minus 1?
I to the power minus 1. Minus 1.
Все, да. Minus q, 1. NC. So C is 1 plus I minus 1. Hence, our G is square root of Q 1 plus I power minus
А
Q.
как у нас получилось слева как мы слева, что мы переравняли
Поставить
коэффициент?
Q равно единице.
Да.
Это G равно единице.
Такой способ посчитать это.
Да.
Да.
Цыганщина.
Ну, можно было на этом месте его действительно чуть считать.
Кажется, я предлагаю делать внутри листка, это еще больше. Можете посмотреть.
Okay. And now, yes, you have case when Q is
Вообще мы не виноваты.
One modulo 4, when G is just square root of Q. And if it's free, then
Then you get I.
yes, yeah, when we get
And if it's 2, then you get 0.
yes.
Сейчас, а G это по своему смыслу что?
Сумма Гаусса, ладно.
Не-не-не, в смысле... Сейчас. По своему смыслу, в смысле в контексте задачи.
G для
то
простого Q это то же самое, что тау от символа лежанка. Проверьте.
Не-не, это мы проверяли. Это скорее какой смысл в него вложен. То есть что-то он показывает, как у нас, например, вот в прошлой задаче было то, что 1 плюс эпсилон от А плюс эпсилон квадрат от А дает нам количество корней.
G это сумма Гаусса. Она появляется в функциональном уравнении или функции.
Я не помню, просто... Я, к сожалению, просто вот мне названия ничего не говорят. Вот.
Она появляется в функциональном уравнении. Там один из множителей это тау от хи.
Тау от хи наш.
Да.
Хи, где характер нашего
Вот.
лежанки.
Соответственно, когда квадратичный характер, хотя бы когда квадратичный, мы хотим понимать, что у нас там за коэффициент. Вот. Ну и, в общем, разгадка состоит в том, что коэффициент всегда 1. Ну нет, не прям всегда, да? Нет, всегда, да?
Сейчас, в смысле, чему равна вот эта вот сумма для произвольного для конкретного характера?
Да,
Ага,
квадратичного.
ага. Сейчас, то есть, что еще раз? Для любого квадратичного характера выполняется вот это вот. То есть, что сумма всегда будет так, ну, равна вот этому счастью.
Чему? Вот этому?
Вот этому.
Вот этому, да.
Ладно.
Okay. Now we have 3 minutes.
Знаменатели и в степени минус 1, что ли?
Да.
Let me comment the last problem. Give a comment. We want to compute if K is a character modular prime number, we want to compute its value at 1. And you know,
It does not matter if it's prime or not prime. In the formulation, we only have a primitive character, which is odd. Nothing else is required.
We skipped all the function stuff and just
so the
computed
first
tau.
problem, oh, okay.
We
Yes.
can discuss the fifth problem.
Yes, okay. The first problem is more general. So we know that this is sum and from 1 up to infinity. Okay, let me write it as chi of n and to the power minus 1. Yes? This is because this sum is convergent. Okay? And now you how to compute such sum. And the idea is to use these Gauss sums you have such expression that chi of n is equal to 1 over tau of chi conjugate now conjugate sum from 1 up to q chi conjugate of h q of nh. So now if you change chi of n with such sum, you will get
Oops, it's incorrect, right? It should be chi conjugate in the sum. Sorry for that.
yeah. Okay, so yes, it's problem 5a, you have chi conjugate also into the sum. Yes, and now if you substitute this expression here, you will need to compute sum of x. Now n is into this exponent, and it will be such sum eq of nh over n. Yes, sum over n from 1 to infinity. How to compute such sum? This is, but you know that sum of x to the power n over n, it is minus logarithm of 1 minus x. Yes?
You have nh.
Yes, nh. This formula holds if left side converges. So this will be logarithm, and after that logarithm is logarithm of absolute value plus I argument, and I think in problem 5a сейчас, не надо предполагать, что там по модулю 1 по модулю 4, в смысле вот 5а.
Нет, просто нечетный характер и все.
Okay.
You should
Now
group
problem-
together
yes, we
plus
need
n
to
and
know
minus
that
n.
chi of minus 1 is minus 1, yes. Then, okay, yes. So this will have real part and imaginary part, and our character is real, and so, but this multiple is imaginary, so we just need to compute the argument. So if Gauss sum is real, then imaginary part will cancel, and we will compute real part, and then it will be actually the sum of logarithms, sum of logarithms of sines. It will be harder. Okay, so if chi is not odd, and so you can solve problem 5a, and let me give you a small tip about 5b. Yes, we need to finish. And 5b, I think you can write n of 1 in such a way. It is 1 minus 2k over 2 to the power minus 1, and here will be product over, here will be sum over odd integers, yes? Of the same, of chi. Yes, here I computed for Legendre symbol. Let's do it for Legendre symbol. Okay, so just we have this multi.
Да, стоп, еще раз что?
Ну, для двойки.
Не-не-не, вот один минус, да.
Минус символ Лежандра пополам?
Пополам минус первое, это все.
Да, хорошо.
Если множите, а здесь-
Получается в суммировании что?
Ну, по нечетным суммам.
Мгм.
То есть то же самое, только мы вынесли один множитель. And now use just the same for this sum. And you will get expression which includes sum of m less than p over 2 of such gender symbols, and you will see that it is positive if p is free modular 4, and yeah, of course it's 0 if it's not.
So we observe kind of a strange phenomenon. If you look into the quadratic residues modulo p, then they are kind of random. But if you sum up to half of p, then you always have a positive, a non-negative sum. This kind of breaks the randomness, the randomness heuristics.